My name is Nivedita Khole and I'm the Technical Support Engineer in MIDAS IT. So here are the contents of today's webinar session. We are running MIDAS webinar series for Indian education, and we can see over here today's session is on performance-based design. Alright, so today's session is going to include introduction to MIDAS as a company, and then we will look into MIDAS Gen project applications, and after that we will be having a theoretical discussion on performance-based design, and we'll take you through the demonstration using MIDAS Gen software solution. We will look at today's conclusion, and also we will be showing the price list. And after that, we will be having a question answer session. So let us begin with the introduction to MIDAS. MIDAS as a company was established in the year 1989, and since then their software solutions have been distributed in more than 120 number of countries. There are 540 number of employees and more than 18,000 number of clients and more than 16,000 number of users worldwide. MIDAS has its headquarters or main office in South Korea, Seoul, and all over the world there are 9 branches. One is in China, USA, India, Japan, UK, Russia, Singapore, Philippines, and lately we have opened up one in UAE, in Dubai. MIDAS has 2 main business areas. One in engineering consultancy. There is consultancy for bridges, buildings, plant structures, geotechnical and mechanical fields. And as per the requirement of the consultancy, the softwares have been developed. So there is software development which have created bridge engineering softwares, building engineering softwares, geotechnical and mechanical engineering software solutions. So that actually makes MIDAS a big SAE software developer in the field of civil engineering with 4 main family programs. The first family program includes bridges. Bridges will include MIDAS Civil, which is an integrated solution system for bridge and civil structures. It means you can do any type of bridge analysis and design in MIDAS Civil software solution. It's a very intuitive software, and within no period of time you can create simple as well as complicated, small as well as long span bridges in a very short period of time. Then comes MIDAS FEA, which is an advanced nonlinear and detailed analysis system. This is where you can actually do your research work, and it is very easy to use software solution for civil engineers. Coming to the structural family programs, there is MIDAS Gen, which is an integrated system for buildings and general structures. You can do analysis and design of steel as well as RC structures using MIDAS Gen. We will be looking at MIDAS Gen itself today. Then is MIDAS D-Shop, which is an auto drafting and rebar detailing module. Like once you get the design done in MIDAS Gen, it can be imported in D-Shop, which can generate the drawings automatically, and also it can generate bill of materials. There is MIDAS Design Plus, which is a structural component design and detailing tool. This one can perform design of isolated footings by taking the analysis results from the structural software, that is MIDAS Gen. MIDAS Design Plus is also capable of generating drawings and bill of material. Coming to the geotechnical family programs, there is GTS-NX, which is a 3D finite element based geotechnical system. And there is SolveWorks, which is a 2D finite element as well as analytical geotechnical solution for practical design. SolveWorks is mentioned for practical design because it's a very easy to use software solution with 7 smart features, which we will see when we are going to go through one of our webinar series. Coming to the mechanical field, there is MIDAS NFX, which is a total solution for mechanical in structural mechanics and CFD. We are using this software solution in civil engineering field because of impact analysis, which is required, as well as CFD, 3D CFD analysis, which is required for buildings, tall buildings. Alright, so it has actually been proved that the 3D CFD analysis using NFX have given closer results to wind tunnel test results. So that is computational fluid dynamics for you in MIDAS NFX. Coming to MIDAS FX Plus. FX Plus is used where there is complex geometry, and that can be easily generated in FX Plus and imported in all the other MIDAS family solutions. So any type of complicated geometries you have for bridges or a general structure or any type of mechanism, so you can actually generate it using FX Plus, which is a preprocessor for finite element analysis. Alright, so we are done with understanding what all solutions we have for MIDAS. Now let's go ahead to our structural solution, that is MIDAS Gen. MIDAS Gen is a one-stop solution for buildings and general structures. Why we call it as one-stop? It's because we can perform the analysis as well as design of RC as well as steel structures, be it superstructure or substructure or combined. So that's an all-in-one MIDAS Gen software solution for you. So let's look into the next content, that is MIDAS Gen project applications. The applications for buildings would include high-rise structures like Burj Khalifa, which have used MIDAS Gen program specifically for column shortening analysis. The complete analysis and design of Moscow City Palace Tower has been done in MIDAS Gen as a primary software. Gate of the Orient, Gamza Twin Tower are a few more examples or of many examples which have used MIDAS Gen as a primary software for analysis as well as design. Some more applications in spatial structures like the Beijing National Stadium, Beijing Indoor Gymnasium, Jeonju World Cup Stadium, Incheon International Airport. So as you can see, complex geometries as well as complete steel or steel plus RC has been included over here. When it comes to specialty structures, we can see over here some applications like Maritime Museum, Foshan Minsu Stadium, Japan Pavilion in Shanghai Expo, Grand National Theatre. So basically we can not only do the simple frame or simple shear wall kind of a structure, but also there is shell type of structure, and we can also do solid geometries in MIDAS Gen program. So by looking at these applications, you can understand how vast MIDAS Gen is, and you can probably use it for your own project works. Now let's go ahead with the main part of today's webinar session, that is the theoretical discussion and demonstration for performance-based design using pushover and time history analysis. So firstly, we are going to have a small discussion on what is performance-based design, and then we'll go with the pushover analysis. So the topic, as you can see over here, seismic assessment of low to mid-rise RC buildings, is specifically for pushover analysis for performance-based design. let us understand something more about performance-based design. What is performance-based design? Basically, it is to evaluate the performance of the building for a given earthquake level. So you have your earthquake and you're going to look at the performance for that earthquake, and then you need to determine the acceptable level of damage to the structure considering its inelastic behavior for that particular earthquake level. So for seismic analysis, generally the structure does not remain linear for long. It's a very short period for which it is linear. It quickly enters the non-linear phase, and that's why we need to understand the acceptable level of damage. And we can see over here it's written about for that particular earthquake level. This means that for any earthquake level, the inelastic behavior or the non-linear behavior of the structure is different. So that's why we are going to be, that's what performance-based design is. Now let's understand the next part. Why do we have to do performance-based design? Alright, so basically the earthquake, like I mentioned earlier, the design earthquake, it causes non-linear behavior. Generally, when we go for a simple static analysis and design, that time we are considering conservative analysis results, and thus our design becomes conservative. To make the design economical, we need to consider the non-linearity. So yes, so static analysis is also, static linear analysis is what I was talking about actually. So if we go for the code-based static linear analysis, then we are getting conservative design results. If we go for the material non-linearity, then we will definitely get economical design. The next reason why we need to go for performance-based is the design codes. They prescribe criteria for building design, but they do not guarantee the performance. Example of parafeed. Okay, this point means that the code might not give us a guarantee of the performance of the building. For example, let's say it's a parapet. Code tells us that maybe the parapet, the code may tell us basically that the parapet height should be 1 meter, but it's not mandatory that the people staying in that area are like taller, maybe they can fall off, so there's no guarantee. Okay, then next point is design codes cannot quantify the performance criteria, thus give less confidence compared to PBD. That this means that there is just pass or fail given by the design codes, but there is no quantifying, or there's no telling how much it is passing, how much it is failing, which is actually provided to us by the performance-based design. Next, simple discussion between the stakeholders and design professionals for deciding performance criteria based on cost and importance of the structure. We know that the stakeholders, or the person who is actually paying for the building, he would be having certain budgets. So that person would definitely think how much in money he's going to be investing in that building, how important that building is for him. So if he does not have much, then he can actually tell the design professional to design it more economical at a certain damage level. So then in that way the design professionals can perform the analysis and accordingly perform the analysis and provide the design to the stakeholders. So it makes it easier for the stakeholders to come up with a particular design or come up with a particular discussion regarding the building with the design professionals. Next is the study alternatives and deviate from code-based design, since performance can be achieved without code compliance as well. So here it's like you can create different alternatives and actually perform the pushover time history analysis and understand how the structure is going to yield, so that you can actually find out where would be the locations of different or what would be the sizes of different members and locations of different members, like shear walls. And like there are lots of code-based designs that have been provided. You can simply use this performance-based design and deviate from the codes, get a deviation from the code-based designs. Alright, so that's one thing. Next is check the effectiveness of retrofitting without concerns over making the existing building conform the latest code compliance. This point means that every year our codes change. Like recently, IS 1893 has upgraded to 2016. So it has modified, and maybe the older structures, they are not actually compliant with the latest code. So because of this, maybe some retrofitting would be required if those existing buildings are assessed. So in such a case, you can definitely go for the performance-based design and prove that your building is actually safe. Alright, next, it is not practical to retrofit the building with every code update. It's the same thing actually mentioned here in the next point. Alright, so that's about why we need to go for a performance-based design. Now, how can we go for the performance-based design? There are two methods. There is pushover analysis and there is inelastic time history analysis. Pushover analysis, it is the static nonlinear analysis, and inelastic time history analysis is inelastic dynamic analysis, nonlinear dynamic analysis. We will look into both of these topics in further slides. In today's webinar session, we are going to be performing using the performance-based design as per American Standard ASCE 41. So accordingly, let's look at the rehabilitation methods that have been discussed in ASCE 41. So there are two methods. One is simplified rehabilitation method, which is permitted for buildings that conform to one of the model building types contained in table 3.1 of ASCE 41 and all limitations in that table with regard to building size and seismic zone. So that code is one I would like to show. Right, so this is the table 3.1. All these types of structures are there. Usually these buildings that have been mentioned over here in detail are not so common. That's why we're going to go for the next method, that is systematic rehabilitation method. Okay, so the systematic rehabilitation method may be applied to any building and is much better. And let's see what is the method in the systematic rehabilitation. Alright, so the first thing that you need to do is you select the analysis procedure, pushover or time history. Alright, and then you have preliminary rehabilitation scheme. You apply the rehabilitation to the building. Okay, then you analyze the building, including this rehabilitation. Maybe you have increased the reinforcement or the size, concrete cover, or you have used FRPU systems and so on. So all those, this entire building model is rehabilitated in the structural solution itself, and then another analysis is performed to evaluate according to the ASCE 41 requirements, chapter 2 to 9. Alright, so that's about the performance-based design rehabilitation methods as per ASCE 41. Alright, so here we have in front of us a slide which showcases all the seismic analysis procedures that can be done in MIDAS Gen program. Alright, so seismic analysis includes linear as well as non-linear analysis. In the linear analysis, again, there is static and dynamic, as well as in non-linear analysis there is static and dynamic. Alright, so we are going to be doing performance-based design, which is the non-linear analysis. So we will be looking at the pushover analysis and time history analysis in MIDAS Gen. In the earlier webinar sessions, we have seen already the lateral force method, that is linear static, and linear dynamic analysis, that is response spectrum analysis. We have also discussed some part of inelastic time history analysis. However, today we will be looking deeper or looking at it with the perspective of performance-based design. So let us look at the pushover analysis, which is a non-linear static analysis. It's a very simple procedure. It's based on the assumption that structures oscillate predominantly in the first mode or in the lower modes of the vibration during a seismic event. So that's what pushover analysis is. And in MIDAS Gen, it's just a two-step procedure. Simply you have to define the pushover hinge properties, assign them, and you have to go ahead with pushover load cases. Now, it's important to understand when shall we go for the pushover, when shall we go for time history. So over here we have a guideline at the bottom which talks about the strength ratio. Okay, so it's an equation 315 as per ASCE standard. So strength ratio R should be less than system degradation. That is R max. Okay, so this is compared. And also we need to check that the higher mode effects are not significant. Mostly this is satisfied. However, we need to check for higher mode effects are not significant. If they are significant, then we need to go for time history analysis. So this basically is possible when it comes to low to mid-rise structures. So let's understand what these higher mode effects are. This means that firstly we need to perform a modal response of using the first mode. Alright, and we need to also perform the modal analysis of using all the modes, and we need to check of 90% mass participation. Alright, so the first one actually over here has been written for all the modes where 90% mass participation is, and the second response spectrum analysis is to be done for considering only the first modal participation. Alright, now here after we perform these two analyses, we need to check that the higher mode effects are significant if the shear in any story resulting from the first response spectrum analysis exceeds 130% of corresponding story shear from second RS model analysis. So basically the story shear of the combined modal analysis should not be greater than 130% of the single modal analysis. So that's what we need to check, and accordingly decide if we need to go through the pushover or time history analysis. So here we have some more information regarding pushover analysis. Okay, so you've got it on your screens. What is pushover analysis? Basically, earthquake load is applied on the model in an incremental basis. When an element has got plastic moment capacity, when in any element plastic moment capacity is reached, plastic hinge is introduced in the model to account for non-linearity of the material, and as a result we can obtain sequential formation of plastic hinges, and this can help us evaluate the performance characteristic through performance point, which is nothing but the intersection of intersection point of capacity curve and demand curve. Alright, so over here in this image we can see in this image we can see this is the capacity curve and this is our design spectrum. Alright, and this is the location where the performance point is. And this is the maximum inelastic capacity of the structure under given demand for earthquake. Alright, so and as per ASE 41, there are different performance levels. So this is a check for lateral roof drift ratio, and it has been mentioned for different levels of damage. Basically, there is operational level, which has a lateral drift ratio of 0.37. Then there is immediate occupancy level of 0.7, life safety of 2.5, and collapse prevention of 5. So this is how the program is going to be checking. Let us see some more. The the levels, different performance levels have been shown over here in pictorial format. Alright, so if your structure is very important, then you'll go for the operational level, which has no or minimal damage. Then is the immediate occupancy level. So over here the damage for that earthquake will be very minor. Like you can do it, you can just repair it simply. Then there is life safety. Here the structure remains stable and it has some capacity with it. Alright, so this is like can be used wherein the building is not that important. And lastly, there is collapse prevention. The building remains standing, but it's like barely standing. And there is pretty much damage. We need to go for maybe like really huge retrofitting, or maybe collapse it after it's rebuild it after it's done with its damage. So this is from operational to collapse prevention level for very important to less or not important buildings. So this is the FEMA code which we are going to be using in this software solution. So building performance levels are obtained by combining structural and non-structural performance levels. Each building performance level is designated a numeral representing the structural performance level and a letter representing non-structural performance level, that is 1B, 3C, and so on. So this is what we're going to be looking at. Now after the damage, then there is rehabilitation that is required to be done. So on your screen right now, we will look at the rehabilitation strategies. These include local modifications, example jacketing, or we can reduce the irregularities, or we can do some global stiffening like bracing or adding shear walls. Then there is mass reduction like load removal, maybe some non-structural walls can be removed or some heavy masses can be removed, machines maybe. Then seismic isolation also can be performed. Isolators can be introduced in that building. So these are different rehabilitation strategies. Okay, the table C2-1, as you can see over here, this one is the example of possible deformation controlled and force deformation controlled actions. Basically, by looking at this table, we need to understand what is actually checked when it comes to moment frames, shear walls, brace frames, connections, and diaphragms. When you're performing code-based design, that we use the force controlled action, and we look at the shear forces, axial loads for beams, columns, And when it comes to shear walls, we are looking for the actual forces and shear forces and so on. So that's required for the force controlled action. However, when it comes to deformation controlled action using pushover, we can simply check with the moment hinges, moment capacities, and in case of shear walls, either moment or shear capacities. When it comes to shear walls, again, if your shear wall is slender, then you need to go for the moment. If your shear walls are short or squat walls, then you need to go for the shear hinges. So that's what we have in case of deformation controlled action. Alright, now let's go ahead and look into the time history analysis. The time history analysis is usually performed for high-rise structures, but it can be performed for any type of structure. So out of all these 4 types, we're going to be looking at the inelastic time history analysis. Alright, now in case of inelastic time history analysis, the procedure is again very simple. It's a 3-step procedure. We need to define the hinges, assign them. We need to create time history functions. We have 32 inbuilt earthquakes, major earthquakes in MIDAS general program. And we need to go for the load case definitions. Now here there are 2 definitions that you can see on your screen. One is the non-linear static, which is nothing but pushover analysis. What I mean to say is, using time history as well, we can perform the pushover analysis, like the non-linear static analysis. And the second type for PBD, that is performance-based design, is the non-linear direct integration type of analysis. And we need to also provide the ground acceleration in case of seismic analysis. If you would like to do machine vibration analysis, there is dynamic nodal loads and time varying static loads are also available. So time history analysis can be done for all structures and is the most accurate. However, it takes a high period, like it requires huge time for analysis, and also it requires investment of engineering cost. That means we need to have a third-party proof checker for that, and then also that engineer must have considerable judgment and experience to perform the inelastic time history analysis for performance-based design. Let us see how this time history analysis is performed or shall be used. Firstly, we need to have at least 3 data sets of ground motion time history analysis. Okay, time histories, ground motions. Okay, so these 3 data sets. Okay, so basically each data set should have one vertical ground acceleration and 2 horizontal ground accelerations with 5% damping. And site-specific spectrum of the scaled horizontal components shall be constructed. Then the data sets shall be scaled such that the average value of site-specific spectra does not fall below 1.3 times the spectrum for the design earthquake for periods between 0.2 t seconds and 1.5 t seconds. So basically we need to compare the site-specific spectra information with the design earthquake, design spectrum, which is as per the code. And these values should be greater than 1.3 times the spectral values of the design earthquake or the codal earthquake, code-based earthquake. And we need to basically compare the values for 0.2 t seconds to 1.5 times t seconds, where t is the fundamental period of the building. Alright, so this is important part. Next part is information regarding how to take out the results. So here we are having 3 time history data sets, that is the minimum. Then we need to look at the maximum value of each response parameter, like the forces in members or displacement at a specific level, drift, deflection, strength, deformation, so on. And then they shall be used for, these force results shall be used for the design. It's always good to have more than 3 data sets. Basically 7 is a good number. Okay, so where 7 or more time history sets are employed, then we can go with the mean value of each response parameter for each hinge over all time history data sets, and then that can be used for the design purpose. So taking an example of 7 time history data sets and 100 inelastic hinges in the model, then one hinge will have 7 values for each response parameter, that is the demand capacity, ratios for force, displacement, etc. Then we take the average of these 7 values, and now the single hinge has 1 value for each response parameter. Then maximum of 100 mean values for each response parameter, also known as usage ratio, TC, shall be smaller than 1 for design to be acceptable. And then further, this computation is to be done at every time step of, let's say, 0.01 second to 0.02 seconds of nonlinear dynamic analysis. Basically, this is how we can understand the huge procedure required, or the long time taking procedure required for the time history analysis for performance-based design. Now let us go ahead to the demonstration. So let me go and open up MIDAS Gen software solution. We will be firstly looking at the performance-based design using pushover analysis for this structure. Alright, so let me firstly introduce you to the user interface of MIDAS Gen so that you can follow up well with me. Alright, so here we have the ribbon menu at the top, which is divided into different tabs as per the work procedure. From left to right, we start with the modeling, then we apply the boundaries, apply the loads, perform the analysis, check the analysis results. We can go ahead after that with the design and then pushover analysis, and we can get information in the query tab, and we can go ahead for bill of materials and all, and the design reports, dynamic reports in the tools. Alright, so from left to right we finish with everything. Then we have the tree menu, in which the work stream menu is important, and this actually can help us understand what all things have been incorporated in our model. For example, we have this model in front of us. We can understand that for this model, P delta analysis, eigenvalue analysis has been performed. There are 13 stories in total. We have beam type of elements and wall type of elements. Then the material used is M35. We have 3 section properties for edge, interior columns, and separately for beams. Then we have 450 mm of thickness for our shear walls. We can see the support that has been applied to the structure at the bottom of the structure. Then we can see that 100% of dead loads and 25% of live loads have been converted into mass. Self-weight has been applied, floor loads have been applied. Wind load as per IS 875 1987, we also have 2015, has been applied in the X and Y direction. Then there is earthquake load in X direction with positive eccentricity as per 1893 2016. MIDAS Gen is actually most updating software solution. We have all the updated codes in MIDAS Gen program. So you can see 1893 2016 for the static seismic analysis as well as for the dynamic linear analysis. So that is response spectrum function, which has been already defined, and there are two response spectrum load cases. Okay, so this is all that have been done in the model, and the analysis has been performed. We are in the post-processing mode. Now let's go ahead and perform the design of this structure. When it comes to design of the structure, again we have the special provisions for seismic design. That means application of IS 13920, and we have the latest standard as well. In MIDAS Gen program, we can actually get the arrangement of the reinforcement. All we need to do is provide it with the diameters of bars that are available. So now we are going to simply perform the design for beams, columns and walls. I'll be performing batch design. When it comes to IS 13920, we need to comply with the strong column weak beam type of design. So we need to perform beam design first, then column. Alright, so analysis is done and design is being performed for all the beams. Once the beams have been designed, we will get all the reinforcements to be applied to the beam. And by using these reinforcements, the program is going to be able to calculate the yield strength of the entire member and then provide us with the proper inelastic hinge property as per the FEMA code. So we are done with the beam design. We can see the results with for each and every beams, and we can see directly by property over here that all the beams are satisfying, they're okay. So I'm going to be assigning this reinforcement to all the beams by clicking on update rebar. Similarly for the columns. And for the shear walls. So now I've assigned the reinforcements to all the beams, all the columns and the shear walls. Next, after we are done with the design, we will go to the pushover. Now in MIDAS Gen software solution, if you do not know how the pushover analysis is to be performed, then you can at any point of time go to the task pane, which is available in the tree menu, and we can see over here. So this is the pushover analysis task pane, which has given us the information for the required steps. So the steps required for pushover analysis is firstly the pushover global control. So we can directly go to the pushover global control from here instead of going to the pushover tab and then clicking on global control. We are going to be using the non-linear static analysis for initial load with the non-linear static analysis. Alright, then we can see over here there are various options actually available in our upgraded software solution. So I'm going to be unchecking few of the options not required and click on OK. So we are done with the pushover global control. Next is the load case definition. So we'll add the load case definition here. I'll add one in the X direction. Alright, I'll keep 20 number of incremental steps. We can consider the P delta effect in this and the incremental method. So as per the American Standard Eurocode standard, we have to go for the displacement control type of method for pushover analysis, and then we will see about how to displace this structure. There are two options available here. We can displace globally by certain distance, or we can use the master node. Okay, so I have already created a node which is located at the center of the mass of our floor plan. Alright, so this is the node 418. The center of our floor plan can be actually seen over here. Boundary, story diagram. Alright, so this is the center, and we can get the location by going to the query tab. Alright, so I'll undisplay the story diagram. Okay, so I've chosen that node, and the direction of my displacement is dx, and the maximum displacement, firstly we will be assuming it. So let's assume 0.5 meters, 500 mm of displacement. This node is connected to all the nodes in that floor plan using the rigid diaphragm as we just saw. Then no need of stopping the analysis, we'll continue it. Then the load pattern, here we are going to be using the mode shape. So here there is the information, like if in the x direction we are providing the incremental in the x direction, then we need to go for the mode shape for the translation in the x direction. So understanding this mode is important. Let us understand what is the mode, fundamental mode for the translation in x direction. So that's the first mode shape, as you can see over here, 83% in the translation in x direction. So accordingly we are going to be going to the pushover load case, add. Okay, consider P delta, displacement control, master node, that is 418 and 0.5 displacement, uncheck, and mode shape, and that will be the first mode, and apply. So we are done with x direction. Now in the y direction we'll have change of direction, and the node will be the same, and the maximum displacement again the same. However, the mode shape now is going to be the second mode shape. So click on add. Alright, so we have LSX and LSY as the load case for pushover. Then we'll go for define pushover hinge properties. That is the next step. Add. For inelastic behavior of the structure, we can define inelastic hinges. So that's why we are going to be defining them. Let's start with the beam. Alright, so before we go ahead, let me take you to the presentation again, wherein we can understand how the inelastic hinges are applied for the frame components and the shear walls. So firstly, for the frame component, that is beams and columns, we can see over here there are two ways. One is by moment rotation, and second is the moment curvature model. So here we have the elastic beam example, wherein the moment rotation hinges are at the ends at two locations, whereas the moment curvature hinges are located at different integration points. So we can actually call it as a distributed type of inelastic hinge that can be assigned to a member. Okay, so ASCE 41 gives the capacities for chord rotation M theta model only. That means if you would like to compare the status of the hinges, then you need to go for the moment rotation. If you go for moment curvature, then we need to convert it into moment rotation and then compare it with the coded provision. Okay, and moment curvature, that is M5 model, is usually used for fiber hinges. Fiber hinges are nothing but distributed hinges, and the rotation is calculated using the fiber strain values, which can be provided by the software. We will see that, and then we compare it with the acceptance criteria for chord rotation as per ASCE 41. Alright, so we can see over here, this is a table for the concrete beams acceptance criteria. So let me go back to the software so that it will be more relevant. So we are taking the beam column type of element, material is RC, and we are going to be using moment rotation for our beam. It's a skeleton model, and the interaction type will be none for the beams. And we will be using MY hinge, that is the flexural hinge. Okay, and that will be both at both the ends, I and JN. Here in MIDAS Gen program, we have an advantage for automatic FEMA hinge calculation. So there is FEMA which can automatically calculate the yield strength value after we assign it to the beams, and it will include the reinforcement that have been assigned to the beams. So we will see after we are assigning. Okay, that is it. And next important part is about the different acceptance criteria that are given over here. Apply. That's done for the beam. Similarly, we have column. Column again, we will use moment rotation, hinge, and we will use PMM status interaction type. Okay, so we can have axial as well in this, and we can look at the properties which again can be automatically calculated by the program. That means the yield strength can be automatically calculated by the program, and accordingly the acceptance criteria. So that is assigned first, and the yield surface properties can be seen right over here, which will be modified after we assign it to the member. So we can see some more information. This is the information provided by the code for the acceptance criteria. Let me get back to the presentation. So we can see over here different acceptance criteria which also will be incorporated or have been incorporated over here by the program. Alright, so we'll apply the column. Next is the shear walls. Okay, so let me get to the slide for the shear walls. Shear walls and coupling beams, wherein we are checking only for actual bending capacity. This is for the cinder walls, and if we have got squat walls, then we go for the shear capacity. So when it comes to the actual bending capacity, we look for the acceptance criteria as shown over here. Now it is shear walls are actually best modeled, or inelastic hinges for shear walls are best modeled with the fiber model. So for the fiber model, we need to go for the moment curvature type. There is wall. I'll just change the name to wall. Okay, so wall, moment curvature, distributed one, and we'll see over here MCPM wall. Then further we can define the fiber hinges for the shear wall. So for that we will add. So here let's name it as wall itself and simply import the wall that has been already modeled. Then further select the regions and divide the section into number of parts. And over here we need to assign concrete property separate and steel reinforcement property separate. So we need to define firstly the inelastic material properties. So firstly let's define the concrete. Okay, we have different hysteresis models over here for our concrete. We even have Mandarin model for confined and unconfined concrete. For now I'm going to be using the Japanese concrete standard specification. Right, so I've got some values which I'll be inputting over here from one of the already created files. Apply, and one for steel reinforcement. We'll be using Manigato Pinto model with 455,000 kilonewton per meter square as the yield strength and elasticity as 2.9E8, and the B value is 0.1. Okay, close. Now the type 1 is concrete and type 2 is steel, and accordingly we are going to be dividing the section Right? Section has been divided with type 1. Next is create rebars. Select type 2, which is steel reinforcement, and now the reinforcement that have been already designed can be imported over here. So we got the reinforcement that has been taken by the program itself. And then we can click on OK. We are done with the wall fiber hinges, hinge definition. Over here we have different components. So we can see again over here there is auto calculation for the yield strength of our shear wall. This is for FX and as well as FY. It's a membrane type of shear wall that we have, and after that we'll click on OK. So here we go, we are done with our beam hinge definition column as well as wall. After that we are going to be assigning the pushover hinge properties. So for assigning pushover hinge properties, I'll be simply selecting or by double clicking all the beams property and clicking on apply. Selecting the interior and the exterior columns, selecting column hinge property and apply. And for the walls, I'll be checking on for the wall and apply. Alright, now let us see how the program has automatically assigned the yield properties. Alright, so we have over here the yield strength calculated by the program automatically right in front of you, so no need to actually calculate by yourself and then provide user defined. No need to do that. You can get it all done by the program automatically. Alright, so we are done with these steps. Now we can go ahead and we go to the task pane. So yeah, we are done with the required steps. We can go ahead to perform the pushover analysis. So this is basically the procedure for pushover analysis in MIDAS Gen program. It will not take much time to perform the analysis. So after the analysis has been performed, we can get to see the pushover curve right in front of us. This is for the Y direction load case, pushover load case. So we have got our capacity curve. Now let's look at the demand spectrum. So let's see the performance point by putting the design spectrum. The design spectrum can be defined from here. By default, we have defined in the response spectrum analysis, we had defined already the IS-189 2016 seismic zone 5 medium soil type with the response reduction factor of 3. Okay, and this one is being compared with the capacity curve that we have over here. Next result is the hinge status. So in the Y direction, in different time steps, we can get to see the performance. The performance is immediate occupancy, life safety, collapse prevention types. We can go at different steps and we can look at the hinge status. So as you can see over here, in the first step it's fine, but in the second step we're getting the failure of one of the hinges at the bottom. We can also get the status of yielding as per the FEMA standard, and this information was actually from the properties, hinge properties that have been automatically defined by the program right over here. According to this information, the program has provided us with the contours and the legend by taking this particular yield strength, and the performance point, or rather the performance of the hinges also have been shown with respect to the acceptance criteria that are given over right over here. We can see the animation of time step incrementation. And save it in a .avi file format. Alright, so after we're done with the pushover, now let's go ahead and look at an example for the time history analysis. So this is the structure for which we're going to perform the time history analysis. We have already assigned reinforcement for the beams, columns and the walls. The next step would be to go to the properties and define the inelastic hinges and assign them to the beams, columns and shear walls. So we click on add, provide the beam inelastic hinge property with moment rotation curve, skeleton model, no interaction, my at both I and j end, and the properties will be automatically calculated by the program. That means the yield strength will be automatically calculated by the program. And then the ductility factors or the deformation indices are provided right over here, which can be also modified. So that's for the beam. Next, for the column, this will have PMM interaction, and we'll see the hinge location for the FX for at I and J end, and MY and MZ at I and J end, and all the information, basically the yield strengths will be automatically calculated by the program depending on the reinforcement and the beam interaction curve of each column. So that's column. Next is the fiber hinges for the walls. So I'll create one for wall, which is membrane type, and it will be having fiber, which is the moment curvature type of definition. And further we'll go ahead and create the fiber hinges for the shear wall. So the procedure is pretty much the same. We can have different fiber hinges for different walls, for different wall IDs and different story levels. So I'm going to be importing this wall 1 and setting up the regions and dividing this section for the type 1 concrete and type 2 as steel, 25, and let's make this as 2 and then divide. Then create the rebars either by using points, linear or circular type. Type 2 is the inelastic material property, and I import the rebar from the reinforcement assigned by the program, and I click on OK. So we're done with one of the fiber hinges for walls. And next is the different components. So the number of sections for which we want to check the results for can be modified. It can be 3 numbers or 4 numbers, 5 numbers, as much as you would like. Alright, so that's about the properties. Again, we can ask the program to automatically calculate the yield strengths for the axial as well as for the moments, in plane moments. After the definition, we will go ahead and assign the inelastic hinge properties. Now we can go to this command and then assign, or we can even directly use these sections. Like for example, I can select all these column sections from here and drag and drop the inelastic hinge property from the workstream menu, and that's how we can get it assigned. So it's that easy. Simply select and drag and drop, and similarly we can select the shear walls and drag and drop the wall property. So that's done. Now let's look at the properties or the yield strength that has been calculated by the program automatically. So this is for the columns. The strengths have been taken by the program automatically. Alright. Now let's go ahead to the loads tab and start with the time history analysis definitions. So firstly we define the load case. Time history load case, which will be non-linear direct integration type. for performance-based design specifically, with time as 20 seconds and time increment as 0.1 is fine. And further, we are going to be using the damping method as mass and stiffness proportion. We do have other options like strain energy proportion and modal type. So I've got some values over here for our mass proportional and stiffness proportional type of damping, which is 5%. And after that, we can go ahead and click on OK, close. The next part is the time history function definition. So we can see over here that in MIDAS Gen program there are inbuilt 32 major earthquakes, and for each earthquake we have got the X, Y, Z directions, time history accelerations. So right now let's define Y. One set will have X, Y, and Z direction for accelerations. So this is X direction now, and lastly for the Z direction. Okay, so time history functions have been defined. Next part is the ground acceleration definition. So we assign the time history data in the X, Y, and Z direction and click on add. We are done with the time history analysis data. Now we can simply go ahead to the analysis tab and perform the analysis. Right, so the analysis has already been performed, and we can see 347.75 seconds was required to perform the time history analysis of such a structure with so many hinge definitions. Alright, now let's take a look at the time history results, which include the forces, deformations, and so on at the time steps as required, different time steps. We can look at the MY component, that is the flexural component, at different times. And that was the eccentricity, the acceleration X direction. Similarly, we can look at the results in the Y direction and the Z direction. Let us take a look at the time history inelastic hinge status results. Okay, so we can see the deformation level. We can look at the status of yielding, RY, flexural status of yielding. So this is how the yielding will take place. We can actually look at the legend to understand what is the linear hinge or what is how the yielding is taking place. So basically dark blue is linear, then there's first yield, second yield, third yield, and this all information is depending on the yielding criteria provided in the hinge properties. Can take a look at the fiber hinge status as well, result of fiber section. So for that we will activate the walls and we'll take a look at one of the walls. Alright, so we can just simply select the wall right over here, the result or the fibers that we want to look at the result of, and we can choose the positions, 3 positions that we had asked for. Then let's plot a graph of time with respect to stress, and then we can say plot graph. So this is the stress graph. We can plot the graph for the strain as well. So the strain and the stress values are given in the form of table, time history table, which can be copy pasted into Excel sheets. So we can see right over here how the status of that particular shear wall was elastic first, and then it went to cracking, and then it was fully cracked. And so on. So basically these are the results at every time step, and we can also do the animation of the yielding of our fibers. And once we get the fiber strain values, we can then further go ahead and get the moment rotation values, which can be further compared with the AC 41 criteria for shear wall. So this is about the time history analysis results for performance-based design. Let us go back to the presentation. So after we have understood damage level, then we can go ahead with the rehabilitation measures. When it comes to RC moments, then we have got jacketing with concrete, steel or fibers, external post-tension reinforcement, improvement of deficient existing rebar by removing the concrete cover, providing the rebar, and then placing the coating again. There is adding or modifying lateral force resting systems like shear walls, mass reductions, etc. When it comes to a shear wall, then we can go with the addition of RC or steel sections at the boundary of the components, at the boundary components, which increases the flexural capacity of the shear wall. We can also provide confinement jacket at the wall boundary. Then we can increase the shear strength of the web of the wall by casting additional RC wall adjacent to the existing wall. We can also do enhancement of the connections when it comes to precast walls. Lastly, let's look at the conclusion and the price list of MIDAS Gen. In the conclusion, let's look at the benefits. All types of seismic analysis, linear, non-linear, static, dynamic analysis can be performed in Gen. There is automatic FEMA hinge definition in pushover analysis that considers the effect of reinforcement assigned to the members. Fiber hinge definition is available for shear walls, which is a type of distributed hinges. When it comes to pushover analysis procedure, you simply go to the task pane and use the steps. When it comes to time history analysis, we have 32 built-in seismic accelerations. When it comes to the results, there are intuitive results for performance-based design such as performance point, hinge status, fiber strain results, etc. MIDAS Gen is a research-oriented analysis and design all-in-one software solutions. You can definitely take the most advantage of the software and make our country proud. Coming to the price list, we have MIDAS family programs, structural package, bridge package, planet element, and geotechnical package for research users. When it comes to a structural package, which includes Gen, Design Plus, and D-Shop, we have package for 5 users and unlimited users. Alright, thank you very much for attending the webinar session. Hope you agree with the benefits of MIDAS Gen. If you have any questions, then you can write to us on globalsupport.midasuser.com. Thank you again for attending the webinar session. Have a great day.